Hello. In this video, we're going to introduce the residue theorem. We're going to talk about where it comes from, what it means, and we'll see a few examples of it applied to functions and contour integrals. To start off with, we're going to start with an overview, some of the highlights of contour integration we've seen so far in the course. We're going to be talking always about a simple closed curve. You'll remember that at the beginning of our discussion of integration, we talked about how you would go about actually computing a contour integral using a brute force approach. If you're integrating around the contour C, what you would usually do is parameterize C, put it in terms of a parameter variable, say t, and then you would feed that parameterization into your function, and for z and the dz, we'd rewrite the integral in terms of t. And then we would have an integral that we could break up into the real and imaginary parts, and those parts would just be integrals of a single real variable, so you can compute them using your integration techniques from past courses. This wasn't quite satisfying, though, to us. We knew that there were some shortcuts coming. The first one that gave us an idea that there would be some shortcuts was the Cauchy-Residue Theorem. This one said simply that if you had a function f of z that was analytic everywhere inside and on a simple closed contour C, then the integral around that contour would be 0. Now, right around that same time, we saw that there was a rule for integrating 1 over a power of z minus z naught. Now, this function is not analytic inside the function C, or inside the contour C, if C contains the point z naught. However, there is a nice, simple form for the answer. If the exponent on z minus z naught in the denominator was exactly equal to 1, then integrating that function around the contour C would give you an answer of 2 pi I, always, no matter which shape the contour had. On the other hand, if the power on z minus z naught was any integer other than 1, the answer would be 0. Now, we found a more powerful version of this rule in Cauchy's integral formulas. The original and then the integral formula for derivatives, which have been sort of rewritten and compressed into this formula here. If you want to compute the integral of f of z over a denominator of that form along a simple closed contour C, then all you have to do is take 2 pi I times it by the n-1th derivative evaluated at z naught and put it over n-1 factorial. Now, this is just a rewriting of that familiar integral formula that you've worked with. But one thing that has probably struck you as we've gone through all of our contour integrations is how often the quantity 2 pi I shows up. We saw it in particular with this rule. We saw it with a couple of the integrals that we computed directly. And the Cauchy integrals formula, integral formulas, both have a 2 pi I involved as well. Now, when we introduce the residue theorem, we're going to give you sort of a more general theorem that will explain a lot of these things, and it will involve the 2 pi I. Now, here's what it looks like. Suppose that C is a simple closed contour contained in the interior of a simply connected domain D. If F happens to be analytic everywhere on and within the contour C, except possibly for at a finite number of isolated singularities inside C, then the integral of f around C is going to be equal to 2 pi I times the sum of the residues of the function at those singularities. All right, now we haven't defined actually what a residue is, but the residue theorem, which is what we call this, says simply if you want to find the integral of a function f along a simply closed contour that's oriented in the positive direction, all you need to do is find the residue of the function at each of the isolated singularities, add them together, and then times by 2 pi. So what exactly is a residue? Well, the definition of a residue is simply the coefficient a sub minus 1 in the Laurent series centered at the singularity you're talking about. So for instance, if I wanted to find the residue of f at a point z naught, what I would do is expand f in a Laurent series centered at that point z naught. So we see powers of z minus z naught everywhere. The residue is precisely this coefficient that sits above z minus z naught to the first power. Now, if we don't want to explain what we mean by a sub minus 1 or write out the terms of the series like this, we'll often use a special notation. We'll write the residue of f of z at z naught to stand for this coefficient, this residue. All right, now taking a look at a couple of examples. Let's start with the function 1 over z minus 1 cubed times 1 times z minus 2 squared. Now this function has singularities at z equals 1 and z equals 2. If we wanted to find the residue at z equals 1, I would just take that function and expand it in terms of powers of z minus 1. And the Laurent series has a 3 sitting in this spot above z minus 1 to the first power. So 3 is the coefficient a minus 1, and 3 is defined to be the residue of this function at 1. Now I also have a singularity at 2. If I wanted to find the residue at 2, I can't do it from what's written here based on our definition. What we would have to do is rewrite the series as rewrite the function as a Laurent series centered at 2, and then we could read off the appropriate coefficient and find the residue at 2. But the residue at 1 is 3. And moving on to the next function, the cosine of 1 over z has a Laurent series you can find by taking the usual cosine of expansion and substituting 1 over z in for z. Now the expansion will look something like this, and if we want to find the residue, remember that the residue is the coefficient that sits above z minus z naught. The singularity here is 0, and our expansion here is centered at 0. So the residue will be whatever coefficient sits above z minus 0, or in other words, just above z. Now the term that has just z in the denominator would fit in here if we had one, but we don't have one. So what we're going to do is interpret this as saying 1 plus 0 over z minus 1 over 2 factorial z squared, and so on. Since we have a 0 numerator in that invisible term, we know that the residue is going to be 0. Now similarly, if we take the function sine of z over z and find its Laurent series centered at 0, which is the singularity, we'll get this expression here. Now this expression doesn't have a principal part, so there is no a sub minus 1 term involved. So again, we're just going to say that the residue is equal to 0. All right, now what can we do with these residues? Well, the residue theorem says, remember, that if you have a contour integral and you have singularities enclosed in your contour C, then the value of the integral along that contour will just be 2 pi I times the sum of the residue of the function at each of those enclosed singularities. So let's take as an example our circle to be that with a center of 0 and a radius of 1.5. Now we're going to suppose that we orient that in the positive direction, counterclockwise, and we're going to integrate each of these functions going around that circle. Now the residue theorem says that to find that integral, we actually don't need to do anything with the integral. We just need to find the residue of the functions at each of those singularities, add them together, and times by 2 pi. So looking at the first function, remember that the singularities are at 1 and at 2. Now the circle, modulus of z equals 1.5, actually only encloses the singularity z equals 1. So what I'll do is find the residue of the function at 1, which on the previous slide we saw it to be 3, and I'll just feed this into the expression. The value of the integral should be 2 pi I times 3, and therefore I get an answer of 6 pi I. Now for the function cosine of 1 over z, which had a singularity at 0, the residue we saw was equal to 0. Feeding that into the formula, we'll have 2 pi I times 0, and so our value of our integral is 0. Similarly, since the residue of sine over z at 0 was equal to 0, the integral of sine of z over z along the contour C will equal 0 as well. Now as you take a look at this, you start to see why the residue theorem is such a powerful result. You'll recall that the Cauchy integral formula and the Cauchy integral formula for derivatives could have helped you evaluate this integral there, and they could have also evaluated this integral here if you had been able to break it up into partial fractions, say. But none of those theorems could have touched this integral, and trying to do it in a brute force way would also have been doomed to failure, because cosine of 1 over z is just not a very nice function when it comes to trying to apply those theorems. It doesn't have the right form we would need. But the residue theorem makes very quick work of that integral, and so it's very handy. Now, as you go through and you apply this theorem, you'll find that it's a pretty simple idea. You just take 2 pi I times by the value of the residue of the function at each singularity that is enclosed by your contour. The hard part, if there is a hard part, will be actually finding the residue of the function at those singularities. Now, you can search online videos. We'll also talk in class about some shortcuts for how to do that. But once you find those residues, the residue theorem itself is actually pretty simple. We're going to end the video now by talking about where the residue theorem actually comes from. As we saw, it's a lot more powerful than some of the other theorems we've previously dealt with. So what makes it tick? Well, the short answer is Laurent's theorem. The residue, remember, is defined as a coefficient in the Laurent series. And you'll remember that in Laurent's theorem, we had a formula for the coefficient a sub k. We said that no matter what integer k you look at, a sub k is 1 over 2 pi I times the value of this integral there. Now, because this is valid for all values of k, we can go ahead and plug -1 in for k. When we do that, that will make the denominator just equal to 1, actually. And so if we were to solve for the integral, we will get 2 pi I times a sub -1, or in other words, 2 pi I times the residue. Now, using what our book calls the Cauchy integral theorem for multiply connected domains, we get exactly the expression there. Now, that's all there is to proving the residue theorem, but a lot of work went into finding these coefficients for the Laurent series. So as you go back and reread the proof of the Laurent theorem, you'll see that we used a lot of facts, the Cauchy integral formula, we used the ML inequality, and so on. But that's it. All right, so have a look at some of the problems. Take a look at what your book says about computing the residue, and we'll see you next time.